So if you're an engineering student taking fluid mechanics, this is the type of problem that you will most likely have to solve. Or if you're just interested in how hydrostatic pressure and hydrostatic forces work, I'll walk you through how that's done. So if we look at this problem, we have this gate, AB, that starts 4 feet below the surface of the water. The gate is 6 feet in height, and it's also 3 feet wide. So first thing to know is hydrostatic pressure increases linearly with depth. We solve for it just by taking the unit weight of water times the depth. So if we're working in English units, you'll have 62.4 pounds per feet cubed times the depth. And if you multiply that together, that's going to give you pounds per foot squared. That's going to give you a pressure. So the first thing that we need to do, if we want to know the force on that gate, we need to find the pressure at the center of gravity of the gate. So for a rectangular shape, this gate is rectangular, so for the rectangular shape, we need to take into account the first 4 feet before the gate starts, before the top of the gate. But since it's a rectangular shape, we know that the center of gravity is going to be right in the middle of this 6 foot high gate. So we just take the 4 plus 3 feet, and that gives us 7 feet. So we plug that into our equation, we get 62.4 pounds per feet cubed times 7 feet. That gives us 436.8 pounds per feet squared. So now we know the pressure at 7 feet. And we want to know what the force is. So we take that pressure and multiply it times the area of the gate. And if you remember, the gate's 6 feet high, 3 feet wide, that's going to give you 18 feet squared. Multiply that times the pressure at the center of gravity of the gate. And that gives you 7,862.4 pounds. There are times when you're going to have to know where does the resultant force act. And the simple answer to that is that it's going to act at the center of pressure. This is the equation that you use for the center of pressure. It looks like a lot, but it's really not that bad. That first term is the moment of inertia about the center of gravity, and then you divide that by the depth to the center of gravity times the area, and then you just add it to the center of gravity. So the moment of inertia for a rectangle is going to be the base, which is 3 feet, times the height, which is 6 feet, and then you cube the height, and then you divide it by 12, and you get 54. Then when you plug the rest of the terms into the equation, you get 54 divided by, remember that the depth to the center of gravity was 7 feet, times the area, which was 18 feet, and then you add that to the depth to the center of gravity, again, which is 7 feet. And you get that at 7.43 feet from the water surface. So the center of pressure is at 7.43 feet of depth. The center of gravity was at 7 feet of depth. So the center of pressure is about 0.43 feet below the center of gravity. As you study this formula, you can see that as the depth increases, that first term, that moment of inertia divided by the depth of the center of gravity times the area, is going to get smaller. The reason is that the moment of inertia about center of gravity is a constant no matter what depth it is, and the area is going to be a constant, but that depth to the center of gravity is going to get larger and larger, which is going to make that term smaller and smaller. So as you start working with very, very large depths, you can see that first term is going to become very small, which is going to make the center of pressure very close to the center of gravity. So again, if you're going to be taking a fluid mechanics course, hopefully you'll find this video helpful. If you did, go ahead and give it a like, or feel free to subscribe to the channel, and thanks for watching.